we're pushing a little further on this idea of simple harmonic motion. We just thought about it in very simple terms yesterday. And now we're going to see if we can understand some of the intricacies of it, especially when we think about it in slightly different circumstances. Okay. Now to begin, it always helps, we're in applications of calculus to the physical world, it always helps to have a picture in your mind of what this is, right? Now we talked about some of the examples before, like heartbeats and tides and that kind of thing. But particularly I want to go after the idea we developed yesterday. I think the most important crucial idea that we got was, for a bit of a spoiler, the differential equation of simple harmonic motion, right? So instead of expressing acceleration in terms of time, we said we could express it in terms of displacement. What was the equation? Negative n squared x, right? Now what we interpreted that to mean is that the further away you are in one direction, the more you're being pushed in the opposite direction. Say that again. The further you are in one direction, perhaps you're positive, right? The more you're being pushed in the other direction, negative, right? And vice versa, okay? So we had the wine glass for rates of change, and we had the tennis ball for straight line motion. So I thought, okay, what's a picture? What's something I can give you? Something from like everyday life, where the further you get away from something, the more you get pushed the other way. This is a bit weird, actually. I was reflecting on this. I thought, oh, in physics, usually it's the other way around. Like, the further away you get from something, the force that's acting on you tends to decrease, right? Like, say, light to your eye, it's actually the inverse square law. The further away you are, the less it's acting on you. Or gravity, the further away you are from something, the less it's pulling on you, okay? But then I realized, no, actually, there's a very common example that we have. Actually, I brought one in my pocket. Actually, I brought 3 in my pocket. I had to bring 3 because I wasn't sure if one would break on me. Rubber bands. We know how rubber bands work, right? So if you have, say, center of motion. Here's my center of motion, okay? Left hand. And you have a particle, okay? And it's moving around. I'm just thinking out straight line, right? So the further that the particle, this hand, is from the center of motion, this hand, right? The further away you are, the more you're being pulled in the other direction, right? Like you can see how I'm being, that's about as far as I can go. I'm kind of scared to snap it, but I'm also not that strong. So what's happening? I'm close to, or from your perspective, I'm further off to the left, right? That might be negative, right? So I'm being pushed, there's a force acting on me, accelerating me toward the right, in the positive direction. And off I go. Now what happens is, as I get accelerated, the further I go in, eventually I get to a point like here, what force is acting on my particle? Answer, nothing, because I'm there, it's comfortable, right? But the thing is, I was moving when I got to that point. So I shoot past the center of motion, I go back over to the other way, right? But once I get to this side, the opposite thing happens, right? The further I get this way, the more I get pushed back toward the center of motion and over again, right? So I hope, rather than, the problem with calculus is thinking it's all letters, right? You need a picture in your head for what does this actually represent. So the picture I have in my head is a rubber band. I hope that makes sense.